let's get started. We are in the fifth segment of module 2, where we've been talking about random variables, and in particular we have talked about the expectation of a random variable and conditional expectation. Today, this segment and the next segment, we're going to talk about some algorithmic ideas. So that's hopefully a good change. So we're going to be talking about geometric random variables, and then we'll apply them to understanding this problem called coupon collectors problem, and that's going to be the topic for today. And of course, we've already seen what the geometric random variable, so in that sense we will just revisit it, and we will understand one important property of this random variable called the memoryless property, and then we'll work out the expectation, understand the coupon collectors problem, and analyze its expected time. Okay. So let's revisit the definition of the geometric random variable. So the best way to illustrate this is it's the number of flips of a coin with some bias p until you get the first heads. Okay. So this geometric random variable comes with a parameter p, and that shows up in this definition, this intuitive definition. More formally, if you have a geometric random variable x, it has a support of 1, 2, 3 and so on, all the integers starting from 1. When I say support, what that means is these are the values for which the probability is non-zero. So for I equal to values ranging from 1 onwards, what is the probability that the random variable x takes the value I? That means the previous I minus 1 flips must have been heads, and that is why you have 1 minus p. This is the probability that you get a tails raised to the power I minus 1, followed by the probability that you get a heads. So this is the formal definition of the geometric random variable. So if it is a proper distribution, you need to have this property that the probability of the sample space should equal 1. Okay. And let's see if we can verify that. And so that you can verify just by summing over all possible elements in the sample space, probability that x takes that value corresponding to that I. And so now we apply the definition, which we have already seen before, and then notice that you can this is essentially, let's see what this is over here. It's basically the sum of a geometric series. So if you apply that formula, you end up getting a 1. So that fits our requirement that the probability of the sample space must be a 1. Then comes the very important property, the memoryless property. This is a very crucial property. It's sometimes can be a little unintuitive, and what this means is that, let's say let's go back to the tossing of coins way of looking at this distribution. If you've tossed the coin a few times and you've been repeatedly getting tails, okay, and let's say you've done this for 5 times, you've repeatedly gotten 5 tails, and let's say, okay, then does that history have any bearing on how many more coin tosses you will need before you get the heads? And as it turns out, history won't have any bearing here, because these are independent coin flips. Okay, and that's the intuition that this memoryless property is capturing. The previous coin tosses, if you are unlucky enough to have gotten tails, will not somehow influence you to get heads quickly. Okay. And this is something that goes counter to a lot of our thinking, because people talk about things like oh, I've had I've had good things happen to me, I'm now worried about something bad happening, or I've had bad things happening to me, I ought to be getting a good thing sometime soon. If this sort of a memorylessness property shows up in life as well, then that won't be the case. I don't know whether it shows up in life or not, but in this distribution it is completely memoryless, at least. Okay, so let's formally see why that's the case. So how do we express that formally? So we are asking, what is the probability of x equal to some I plus k, given that x is greater than k? What does that mean? So for the first k coin tosses you have had tails, you have been able to observe that. Given that, you know that x therefore has to be some value greater than k. Okay. So, what is this conditional probability on the left hand side? Now, the right hand side, look, it has no the k is completely eliminated. So, the fact that you have seen k coin tosses is completely eliminated on the right hand side. It is just the probability that x equal to I. So, let us see why this is true in a formal way. So, the left hand side we take it and we just apply the formula for conditional probability. Then so on in the numerator is what do we have? It's the probability that x equal to I plus k intersected with the event that x is greater than k. Okay. So, if x is equal to I plus k and I and k are both positive quantities, clearly what you have on the numerator is basically just what happens. You have to get I plus k minus 1 tails followed by the heads, and x has to be greater than k. Okay. And in the denominator we have so that is the numerator. In the denominator let us be a little bit careful. So, what you are saying is the probability that x is greater than k. So, if x is greater than k, it can take the value k plus 1, k plus 2 and so on. So, you have to sum it over all those possibilities. And so, we run it through a summation starting from j equal to k to infinity. So, the first j coin tosses have to be tails followed by a heads. Of course, you have two p's in the one in the numerator and one in the denominator. So, they will cancel out. And one thing that I would like you to work it out on your own is basically that this summation, if you work through it, is going to end up being 1 minus p raised to the k divided by p. So, it will come out this way in this derivation. So, when you work it out, it is going to be so what happens over here 1 minus p raised to the k will cancel out with this k over here. So, you will get 1 minus p raised to the I minus 1 times this p, which is nothing but the probability that x equal to I. So, this is formally verifying our intuition of the memoryless property. So, now let us look at the geometric random variable and let us ask what is the expectation of the geometric random variable. We want to claim that it is 1 over p, and this should make intuitive sense. So, now let us say that this geometric random variable, the coin has bias, very small bias. That means it is going to take more coin tosses to get the first head. So, say bias is 1/10. Okay. So, roughly only a tenth of the coin tosses you are going to see is heads. So, you will have to toss roughly 10 times before you see the first head, right, and that is an intuitive statement. So, when we try to formalize it, we will be able to we will state that as expectation of x equal to 1 over p. So, let us see why that is exactly correct. So, when you think of, let us focus on the first coin flip. The first coin flip can either be a tails or a heads. So, let us say that define another random variable y. It is a Bernoulli random variable. So, just it is equal to 0 if the first flip is tails and 1 if the first flip is a heads. Okay. And so, now the expectation of x, you can write it in this fashion. So, now let us say there are two possibilities, either the first flip is a tails, okay, or the first flip is a heads. This might be a little bit easier. So, when the first flip is basically, well, let us actually let us look at this line. Depending on whether you get tails or heads, the expectation becomes conditional on that. So, the expectation of x conditioned on y equal to 0 here, y equal to 1 here. Let us actually see how that plays out. Now, it will be easier to see this part. When y equal to 1, what does that mean? It just means that the very first coin flip was a heads, okay, and this probability itself is p, and then this conditional expectation becomes a 1, because in the very first flip you got a heads. Okay. In this part, the probability is 1 minus p, but what about the conditional expectation? Well, when you say y equal to 0, it means that the first failed. You cannot have a value of x equal to 1 for this in this case. So, we can condition, instead of conditioning on y, we can condition on x being greater than 1, because y x equal to 1 is out of the question now. So, now what is this expectation of x given x greater than 1? When you think about it, now we are applying the memoryless property. X, when it is greater than 1, it's when it's guaranteed that it's greater than 1, has to be at least 1. The first flip has to be a tails, after which entire memory is lost, and you're basically, it's like starting the experiment all over again. Okay. So, this 1 is accounting for the fact that the first coin flip was a tails, and that is completely lost. You have to restart the experiment. So, then you have to add this x. So, this x given x greater than 1 can be written as just x plus 1. Now, we can apply linearity of expectation. So, and I am skipping a step here, linearity of expectation, and then multiply it with 1 minus p, you will get these terms, and you will get a few cancellations. So, p and minus p will cancel out, and so here what, let us actually work this out a little bit carefully. So, this E of x will cancel out with this E of x, this p will cancel out with this p, and so what you will have is p times E of x equal to 1, which will then give us this form. So, this again confirms our intuition that the expectation of the geometric random variable is 1 over p. So, now comes this this very interesting problem, the coupon collectors problem. The way to sort of explain this is, at least is a fun way to think about it. So, let us say you are buying something in the store, and each time you buy you get a nice sticker. Okay. And let us say there are some n different types of stickers, and you want to, and each time you buy this box of chocolates or whatever, you get this sticker, and you get a random sticker out of the n different stickers that the company has made available. And so, you are asking, how many times should I buy these box of chocolates before I get at least one copy of all the n stickers? So, let us state that formally. You are given a collection of n coupons, if you will, stickers, coupons, whatever you want to call it. And then what do? When you buy this box of chocolates, you get one of them. Okay. So, think of it as sampling a random coupon. Okay. And you want to now repeat this process until you have gotten all the possible coupons at least once. Okay. So, maybe the next time you buy, you get this coupon, and the next time you buy, unfortunately you get something that you have already seen. Okay. And next time you get something new. Okay. And then you again get unlucky, you get something you have already seen before, and finally you get to see something, the last coupon. So, at this point you have seen all the 4 different coupons, right. So, that is the coupon collectors problem. And the question is, how many times should we buy the box of chocolates before we get to see all the stickers? Or another way of stating it is, how many iterations of this procedure here should be executed before we have gotten all the coupons? And this is a simple problem that shows up in a lot of sampling situations. So, it is important to understand this. This can be analyzed quite thoroughly, but for now we are going to just focus on understanding the expected number of iterations. Okay. So, this is the theorem we want to prove. Let x be the number of iterations of the coupon collectors problem. So, the number of times you will sample. The expectation of x is equal to some n times ln of n plus a smaller n term. So, how does this proof go? We do this sort of breaking up of x. So, we break up this x into small xi's. Okay. So, in particular xi is the number of iterations after you have seen I minus 1 different coupons, but until you see the ith coupon. Okay. So, let us make sure we understand what this means. Okay. So, this is let us say the timeline, you are sampling over time. Okay. The very first time you buy something, you are going to see something new. So, your x 1 basically is after you have seen 0 different coupons until you see the first new coupon. So, that is just x 1 equal to a 1. Okay. The very first time you buy something, you will get something new. The second time so at this point in time, you have seen one coupon, there are n minus 1 coupons that you have not seen. Okay. So, now you ask, okay, how many times should I buy before I see one more new coupon? That is going to be your x 2. Okay. So, what is the expectation of x 2? If you think about it, it is now going to be a geometric random variable. Your success, your p, is basically n minus 1 over n, because there are n minus 1 coupons you have not seen before out of a total of n, and if you get any one of them, you have seen a new coupon. That is your p value, and what is the expectation of x 2? That is 1 over p. So, that is n over n minus 1, and similarly expectation of x 3, if you work it out, it is going to be n over n minus 2, and so on. So, this pattern will continue on. Okay. And this should fit your intuition, because in early on these quantities are going to be very close to 1. Expectation of x 2 is going to be close to a 1, expectation of x 3 is going to be close to a 1, and so on. Okay. And this should fit your intuition, because early on it is going to be easy to find new coupons. Okay. But as you start collecting coupons, it is going to get harder and harder to see new coupons, because every time you buy, you are going to find a coupon. It is likely that you are going to find a coupon that you have already collected. And in particular, if you look at the very last x n, it is going to, on expectation, take n time before you find that coupon, because you have seen n minus 1, you only have one coupon that you have not seen out of a total of n. So, your p reduces to 1 over n. So, the expectation becomes 1 over p, which is equal to n, okay? And that should fit your intuition. So, now let us know, now that we know these expectations, let us plug them into our understanding of x. So, clearly the capital X is just this is just breaking, clearly we are just breaking time into x 1, x 2 and so on up to x n, right. So, capital X is simply the summation of these xi's, and we can apply the linearity of expectation and apply the formula for E of xi, and so that is going to be summation over I n over n minus I plus 1. And n is common, so you get it out, and summation I 1 over I. What is summation I 1 over I? That is nothing but the nth harmonic number, and we have a formula for that. It's the textbook goes through the details of how this formula is arrived at, but we will skip those details. But essentially nth harmonic number is nothing but it's between ln n and ln n plus 1, and so you can write that as ln n plus theta of 1, and with that we get the result that we want. Yeah.
The typo of the previous slide.
Oh, okay. Where is the typo?
The E of x is theta of n, right?
Theta of 1.
Yeah. So the statement of the
Oh, okay. Yes. Yeah. 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 Thank you. So, with that we conclude the proof of this theorem, and so we can conclude this segment. Just to remind ourselves, we revisited the geometric random variable, showed that the expected value is 1 over p when the parameter is p, and we looked at the coupon collectors problem, and we showed that the expected number of times you need to buy the box of chocolates, if you will, is n ln n plus some theta of n. Next segment we are going to again look at something interesting, again an algorithmic problem, finding the median, or more generally the case selection problem. Okay. Thank you.